In this video, we're going to learn about composition of functions, which is a new way to combine functions. In fact, we're defining a new operation between two functions f and g. So let's start by trying to build some intuition about what this composition of functions is going to look like. Well, we're going to relate this to the idea of evaluating a function at a particular value. So let's say I have the function f of x is x squared and g of x is x plus 1. What does it mean for me to evaluate a function f at the x value of negative 3? Well, this is a well-known operation. We've done this many times. So what I do is I go to the rule of f, and wherever I see the x, I'm going to plug in negative 3 for x. So I get negative 3 in a parenthesis, and that I square, so the answer happens to be 9. So again, what I did here is I went to the rule of f and I replaced x by, and let's use parentheses because we're under a power, by the parentheses negative 3. We're now going to do the same thing, only evaluate at an algebraic expression. So I'm going to now plug g of x into my function f. The same idea is going to work. Well, first, what is g of x? G of x happens to be x plus 1. So we write down x plus 1 here. And now I'm going to perform the exact same operation as I did in the case of evaluating at the constant. Namely, I'm going to look in the rule of f, and I'm going to replace the x now by this quantity, namely the parentheses of x plus 1. So I'm going to have x plus 1, and then as before with the 3, I'm going to have everything squared. So the idea here is very similar to what we had before. If before, when I had the number negative 3, I replaced x by negative 3, in this case here I'm going to replace x by the parentheses x plus 1. So in essence, if you know how to evaluate a function at a number, you also know how to compose two functions. There is no difference. And if you ever get confused, just think, what would I do if I had f of 2 and then replace the same thing? Instead of 2, you would write whatever quantity you have there. So this is the intuitive idea behind composition of functions. We're now going to develop the concept of function composition, and we start by listing the definition. So the composition of a function f with a function g gives us a new function. So that's really important. When I take two functions f and g and I compose them, I'm going to get a new function that I'm going to denote by f composed with g. That open circle is the way we denote the composition of function. What is the rule of this new function? Well, it's going to be given by f composed with g of x is f of g of x. So exactly what we were computing over here is going to give us the composition of functions. So let's look at an example and try to write down what the composition of two functions is. So let's say f of x is x plus 2. And g of x is going to be, say, 4 minus x squared. If I try to compute f composed with g of x, then by definition this is just f of g of x. Notice that I preserved the same order that these are listed in. Namely, I have f composed with g, that turns into f of g of x. The next step is going to be to write down who is g. So you go down and you see that g is 4 minus x squared. And that's what you're going to evaluate in the rule of f. What would you do if you had f of 3? You would have 3 plus 2. So what do I do when I have f of 4 minus x squared? I'm going to have 4 minus x squared and then plus 2. So this turns into 6 minus x squared. On the other hand, if I want to compose g with f in this order, then again by definition, and I write these functions in order, I have g of the second function f of x. So now, what is f of x? F of x is x plus 2. So now I have to evaluate g at x plus 2. What would be g of 5? That would be 4 minus 5 squared. So wherever I see the x, I'm going to replace it by the parentheses x plus 2. So this is 4 minus x plus 2 squared. Trying to simplify this, I'm going to get 4 minus, let's first square, so I have the a plus b squared formula, which gives me a squared plus 2ab, so 4x, plus b squared, so that's 2 squared, which is 4. So now the 4 and this 4 cancel because I have a minus in front of the parentheses, so this turns into negative x squared minus 4x. It's important to realize that this is the first operation that you have seen, even though it's an operation on functions, that is not commutative. What do I mean by that? If I change the order of composition, namely I first compose f with g and then g with f, I will not necessarily get the same answer. Namely, f composed with g in this case is not g composed with f. Again, this is a non-commutative operation. Multiplication or addition, for example, of real numbers is commutative. Namely, the order doesn't matter. If I multiply 2 times 3 or 3 times 2, I will get back the same thing. So now let's try to understand function composition from a theoretical standpoint. Let's see what we're really getting. So let's say that I have, again, the same example, the function f and the function g as we had before. So let's understand what is this object g composed with f that I'm creating. Well, first, we think of the function f independently, and I'm going to start with a certain x value, and f is going to map it to its corresponding y coordinate, which you remember we denote by f of x. So the action of the function f will be as follows, the natural one, it will send x to f of x. Now what we're going to do in a second step is we're going to act with the function g. Now we're not going to restart the process, we're here at f of x, and now I want g to act on this point to take it to its corresponding y value under the action of the rule of g. Well, if that point over there was 2, 2 would be mapped to g of 2, so in this case what I get is g of f of x. So when I have the function f first act on x, it gets mapped to f of x, and if I follow this by the action of g, then this gets sent to g of f of x, which is exactly what g composed with f, this function, does. It's going to take x straight to g of f of x. So if you want to think of it, composition of functions, you can do this as a two-step process. You can first act with the function f, then follow it by the action g, or we can compute the rule of g composed with f and do this in a one-step process rather than taking our time. Here's a numerical example. Let's say that I start off with the x value of, say, 1. Then f is going to map 1 to f of 1, which is 1 plus 2, and that's 3. Now if I pick it up at 3 and act with g on this function, then I'm going to get g of 3, which happens to be 4 minus 3 squared. That's 4 minus 9, so negative 5. However, if I act directly with the function g composed with f going from 1, I'm going to get g composed with f evaluated at 1, and if I plug that into the rule, I will get negative 1 squared minus 4 times 1. So it's negative 1 minus 4, so we get the same negative 5. So we can think of composition of functions as a one-step process. We're getting one function that can go straight from x to g of f of x in one step, rather than having to go through this two-step process if we first apply f and then g. So now let's look at a few examples and try to practice a little bit more how to compose two functions. Let's look at the example. F of x is x over x plus 1 and g of x is x cubed. What is f composed with g of x? Well, we follow the same algorithm. This by definition is f of g of x. Now we write down what is g of x, namely x cubed. So now I evaluate f at x cubed, so I look at the rule of f, and wherever I see an x, I will replace it by x cubed. So if you had f of 5, you will get 5 over 5 plus 1. So with x cubed, you get x cubed over x cubed plus 1. And this is the rule of f composed with g. If I also ask you to figure out what is f composed with g, say evaluated at 0, there's no need to go after the two-step process. You have the rule of f composed with g, so just use it. So what we're going to do is plug 0 in this rule, so we get 0 cubed over 0 cubed plus 1, which is 0 over 1, so that happens to be 0. On the other hand, if I try to compose g with f, then by definition this is going to be g of f of x. So I evaluate g at the rule of f of x, which is x over x plus 1. So looking at the rule of g here, if I had g of 3, you'd have 3 cubed. So I replace the x now by the full parentheses x over x plus 1, everything to the power of 3. So you notice how the x got changed and I replaced it by this parentheses x over x plus 1. What is g composed with f, say evaluated at -1? I will have -1 over -1 plus 1 cubed. And that gives me -1 over 0, so this is an undefined operation. So g composed with f is not defined at this point of -1. Let's look at one more example that is, well, simple, very special. So let's say I have f of x is x plus 2 and g of x is x minus 2. What happens when I compose these functions? Well, f composed with g gives me f of g of x. So I get f of x minus 2. So now I go to the rule of f and evaluate at x minus 2, and I will get x minus 2 and then plus 2. The 2 and the -2 cancel, and I simply get x. We'll see that the same thing happens when I compose g with f. So in this case, I will get g of f of x. F of x happens to be x plus 2, and when I plug in the rule of g, x plus 2, then I have the -2, that 2 brings me back to x. So what is going on here? If I start off at x, f will take me to its corresponding y value, let's say f of x, but then when I act with g on it, it's going to take me usually to g of f of x, but that just gives me back x. So in this case, the action of g, it doesn't matter what x you give me, is always going to be that it really takes this y value back to x. So whatever f does, it will send x to a certain y value, g will send it back to x, so it will undo the action of f. And therefore, we will see later, f and g are going to be called inverse functions of each other, and the way we're going to define that is by saying that when you first apply f and then g, you get back to the same starting point, namely to your x. Finally, an important idea in calculus is being able to decompose a composite function. So we're going to start off with a function h that is rather complicated in its rule, and we're going to try to see which two functions got composed to form h. So we're always going to use the notation f and g, and we're going to want to write h of x as the composition of f and g in this order. Namely, we want to have f of g of x. So we're always going to have g denote the inside function the one function that has been plugged into f, f has been evaluated there, and f will have the name of the outside function. So let's look at an example. Let's say h of x is 1 over x minus 2, everything squared. So which two functions have been composed? So let's look on the inside first. So let's try to identify the inside function g of x. Has anything been plugged inside something else, another function? And yes, in this case, the x minus 2 has been plugged into f of x, which represents the outside function. And what's left over? If I were to delete this 1 minus x, all I get is the parentheses over here squared, and I'm missing the x minus 2. So the way I write down what f of x is whatever is missing is going to be replaced by x. So I have f of x to be 1 over x squared. So when I plug x minus 2, I really do get my answer for h of x. Let's look at a few more examples. Let's say h of x is the cubic root of x squared minus 4. So we're trying to find an inside function, g of x. Can you see anything that's been plugged inside something? And of course, that's going to be the x squared minus 4. And what's left over once I remove that x squared minus 4 is the cubic root, but I need an input of x for it to define a function. And finally, let's say that I have h of x is 1 over x plus 2. This one is a little bit trickier because there doesn't seem to be an inside or an outside, but we can think of the x plus 2 as my inside, and that leaves the function f to be 1 over x. And we notice that the x plus 2 really was plugged in the denominator there as the inside function and turned it into x plus 2.